Imagine you're building a system with millions of users. A single server can't handle it all, so you distribute the load across a cluster. The challenge isn't just spreading the work, but making sure the same request always finds the same data. This is the world of distributed state. Most beginners start with a simple modulo operation, taking the hash of a request ID and dividing it by the number of servers. It works perfectly until it doesn't. In this video, we'll explore consistent hashing, the elegant mathematical solution that allows global scale without the chaos of massive data reshuffling. We'll look at why the standard approach breaks down and how a simple circle can solve one of computer science's most frustrating distribution problems.
Let's look at the standard approach, hash modulo n. If you have 3 servers, a request with a hash of 10 goes to server 1, 11 goes to server 2, 12 goes to server 0. It's predictable. But what happens when your traffic spikes and you need a 4th server? Suddenly, hash 10 modulo 4 is server 2. Hash 11 modulo 4 is server 3. Every single mapping has shifted. In a caching system, this is a disaster. It's a cache miss storm. Your database gets slammed because the servers no longer know where anything is stored. We need a way to add or remove capacity while only moving a fraction of our data.
The foundation of consistent hashing is mapping both our requests and our servers onto the same logical space, a circle. Imagine the range of your hash function, say from 0 to 4 billion, wrapped around into a ring. We no longer care about the absolute number of servers when we calculate the hash. Instead, every request is assigned a position on this ring based solely on its own value. This position remains constant, regardless of how many servers are currently online. This shift in perspective, from a linear array to a circular continuum, is the first step towards true horizontal scalability.
Next, we place our physical servers on that same ring. We hash the server's IP address or name, which gives us a fixed coordinate on the circle. In this example, server A, server B, and server C are spaced out across the hash space. These servers now act as anchors. Because they occupy specific points on the ring, they naturally divide the entire hash space into segments. Each server becomes responsible for the arc of the ring that precedes it. This setup is static. Unless we add or remove a server, these positions never change, providing a stable backbone for our data distribution.
Now, when a request comes in, we hash its ID to find its position on the ring. To find which server should handle it, we simply travel clockwise from the request's position until we hit the first server. This is the nearest neighbor rule. If a request lands between server A and server B, it goes to B. If it lands between B and C, it goes to C. This simple rule ensures that every point on the ring has a deterministic owner. No matter how many times you hash the same request, it will always land in the same spot and travel to the same server.
This is where the magic happens. When we add a new server, server D, we hash its ID and place it on the ring. Let's say it lands between server B and server C. Now, only the requests that fall in the arc between B and D need to move from server C to the new server D. Every other request on the ring continues to go to its original server. In a standard modulo system, nearly 100% of your keys would relocate. In consistent hashing, only 1/n of the keys are affected. This is why it's called consistent. The mapping stays largely the same even as the cluster evolves. In the real world, servers aren't distributed perfectly. If server A and server B land right next to each other, server B might end up doing almost no work, while server C handles a massive arc of the ring. To solve this imbalance, we use virtual nodes. Instead of placing a server on the ring once, we hash it multiple times with different seeds. Server A might appear as A1, A2, and A3 at different points. This averages out the distribution, ensuring that even with a few physical machines, the load is spread evenly across the entire hash space. It's a simple trick that makes the system robust against hotspots. Consistent hashing is the engine behind the world's largest distributed systems. It's how Amazon's DynamoDB stays performant as it scales, how Apache Cassandra manages data across clusters, and how content delivery networks like Akamai route you to the nearest edge server.
By decoupling the hash from the number of servers, we gain the freedom to grow and shrink our infrastructure without breaking the logic of our applications. The next time you scale a cluster, remember the hash ring, the simple circle that keeps the internet's data in place. Thanks for watching.